In our last class, we started discussing about the basic motivation of public key crypto system. So as you all know that in crypto system, we do have mostly two different kinds of crypto system, mostly public key crypto system and private key crypto system. So it depends on the keys. If these two keys are happen to be the same, then we call it symmetric key or private key crypto system. And if these two keys are different, then we call it asymmetric key or public key crypto system. So all happens due to the presence of this bad guy who is always trying to listen, and sometimes he may be little more active to do more malicious work, like he can stop the interaction between these two boy and the girl, or may modify the packets so that something else might be received by this girl. So today's class is basically dedicated to a few attacks on RSA as well as few theoretical proofs of RSA, how this RSA works mathematically. So in my last class, I already mentioned about how RSA works. So RSA is the one of the most celebrated public key crypto system. So it's based on, as you all know, that it's based on the factorization problem. So computationally hard problem. That means it's difficult to factorize two big uh, product of two big prime numbers. So based on that, this RSA crypto system came into picture. So if you go a little back in our last class, we have already mentioned about how this private key crypto system works. For example, one of the oldest private key crypto system was done by Julius Caesar. This is known as Caesarian cipher or CIF cipher. The problem here is, if both of them, if Julius Caesar wants to send some message to one of his subordinate, then both of them, they should carry the same key. But if it happens that both the senders and the receivers, they are actually staying just opposite half of the world, and they do not have any secure channel, then the question is how these two keys can be combined, or how they are going to use the common keys. So that was a problem. And I in my last class, I already mentioned through some example of real life how the public key crypto system can be thought of. For example, in my last class, I have already mentioned about that he is the controller of examination of some university, and he is the external paper setter. So what the external paper setter wants, he wants a very secure way of communication. So when the paper setter makes his question paper, he requires the question paper should reach him in a very secure fashion. The best way it could be done is like he can make the question paper, and personally he will come to visit the controller of examination, and he will give the question paper to the controller of examination. But unfortunately, for most of the cases, if he is one of the external paper setters, then usually he doesn't come personally to give the question paper to the controller of examination, but a kind of person, usually the postman, takes into the account, and he collects the question paper and sends it to the controller of examination. But the controller of examination is very fond of about the security of the whole system. That means he considers that this channel is not secure. So try to compare the situation with the digital world, right? So this guy wants to this guy wants to send some message to this guy through this insecure channel. So the question is how that can be done. So in our last class, we already mentioned about a nice protocol that to do so, the controller of examination will consider two lock and keys, two different lock and keys, and for security purposes, these lock and keys are such that they do not have any duplicate copy. That means you cannot make a duplicate copy of this key of this lock or this key of this lock, but they are two different lock and keys. And I explained you how that can be done. Like, okay, so what he will do, the controller of examination will send a box along with a lock and key through this postman to this question setter. Okay, so the paper setter, when he will complete doing the question setting, then what he will do, he will put the question paper inside the box, and then he will use his own lock and key to lock it and send it back through the postman to the controller of examination. Okay. Now the point is, the controller of examination does not have the lock and key, right? He has the lock, but he doesn't have the key. So the question is how he is going to open this. So the protocol that we have used here, then he will use his second lock and key, and he will make a lock of it, and he will send it back to the paper setter through this postman. Now the paper setter has the key to open the lock. So he will open this lock and he will again send it back to the controller of examination. Now the controller of examination has his own lock and key to open this and to get the question paper. So that was a kind of parallel situation in case of a digital world where the public key crypto system can be thought of. Just now at the beginning of my lecture, I just mentioned that in case of public key crypto system, you have two different keys. One is public, that means these lock and keys are public because he knows this lock and key, and one he keeps with him secret. So at the end, when he is going to decrypt the message, he is using his own lock and key. So he is actually sending the message. That's why he is the sender, he is the receiver, but the infrastructure was actually made by this controller of examination. That means who will be the receiver will make the infrastructure. That means infrastructure will be made by the receiver, while the sender will collect the public key of the receiver and encrypts his message and send the locked message through insecure channel. When he will receive the locked message, he will have his own lock and key. He will use his own lock and key to get the original message. So that's the kind of parallel situation what could be done in case of a digital world. Okay, again the same scenario, and it was for the first time that Diffie and Hellman in 1976 they came up with a nice idea that is known as key agreement protocol, where they are not going to use some public key concept, but what they are going to do after uh, few message sending process through this insecure channel, ultimately at the end of some time they will be able to uh, agree upon a common key. That means both sides they will have the common key. So I will teach you in maybe after 2 or 3 lectures this Diffie-Hellman key exchange protocol in detail, and will show you how another mathematical important problem known as discrete logarithm problem plays an important role here. But unfortunately in 1976 they couldn't come up with any of the public key crypto system, but it was for the first time in 1977 these three great guys, Shamir, Edelman and Rivest, so mid portion was the Rivest, so they came up with the nice protocol that is known as RSA Public Key Crypto System, which is actually based on the famous problem that is known as computationally hard problem, that is known as factorization. So factorization is a computationally hard problem. So as just now mentioned, in case of a sender, so suppose he is the sender and she is the recipient, as just now I mentioned, in case of RSA public key crypto system as well, the recipient should take the initiative first to make the infrastructure. So it works in this way. So first the receiver, so C is the receiver, just I will just make you one more time to, because today we are going to prove it. So we should have this. So she is the recipient receiver and say he is the sender. So just now I have mentioned it should be the duty for the receiver to have to start the protocol. What she is going to do, she is first going to choose two distinct large primes P and Q. So P should not be equal to Q. Then she will compute n equal to P star Q. Then she is going to compute phi n. So in my last class, I have already mentioned she is not going to calculate phi n, but she is going to just compute P minus 1 and q minus 1, and if she is going to make a multiplication of it, that will automatically give the value of phi n. So that was already defined in my classes on number theory required for this public key crypto system. So maybe in third or fourth classes I have discussed in detail about all those things. Then she is going to choose some e such that GCD of e and phi n is 1. So this is Euler Phi function. If you forget about Euler Phi function, the definition is very simple. So for a given positive integer n greater than equal to 1, phi of n is nothing but number of positive integers less than equal to n and relatively prime to n. Relatively prime to n. So that means whose GCD with n is 1. All such positive integers, that means you are basically 1 to n, you collect all those integers who are relatively prime to n. So that number, so this is the number of positive integers. So phi n actually gives you a number. So that value is given by phi n. So the girl then finds some e such that GCD of e and phi n equal to 1. Okay. Then she will compute ED congruent to 1 modulo phi n. Okay. Now she completes her all setup system. Now she is going to make public two things. So she is going to make public, maybe in her web page or somewhere, she is going to put this two value n and e, and she is going to keep with her secretly. So she will keep with her this value of d, actually p and q as well. But p and q will not be required for further use, but d will be required. So this is secretly kept with her, and this is public. So as we are going to use two different kind of keys, unlike the symmetric key crypto system, this is known as public key or asymmetric key. So it's not symmetric because this key and this key, they are different keys. Okay. Now, so all the setup part is done. Now it's the duty for the sender. So the first
Sir,
thing for the,
phi n, sir, definition of phi n less than is equal to n, less than n, sir.
okay,
Less
so
than
in
n.
no, in my class I have already defined. So if you say, so can you just repeat the definition of phi n? Okay, so except for less than equal to, everything is same for you, your definition. Anything else that you want to include here in the definition except for this?
Sir, less than.
Okay, so your is strictly less than n, right?
Yes, sir.
Okay, now
For
tell me what
five,
is, yes,
five, sir. If I take n is equal to 5, then
yes,
five is 1, 2, 3, and 4.
okay,
5.
okay, fine. So if you take strictly less than, so your definition is strictly less than. Now tell me what is the value of phi of 1? In your definition, what is the value of phi of 1?
Phi
So
of 1.
number of positive integers strictly less than 1 and relatively prime to 1, right? So how many are
Yes.
there? How many numbers are there? Strictly less than 1 as well as positive integer? How many? So you will not, so in your case, this value will be 0, but you know that phi of 1 is 1. So if you are going to give this definition strictly less than, then you have to include this as well within your definition. Okay. So
Okay, sir.
and
Oh,
phi of 1 equal to 1. But to avoid this, I just made it strictly, not strictly less than, but less than equal to 1. In that case, what happening, except for 1, if n value is 1, then it's fine. Otherwise, if n is not 1, no number other than 1 is relatively prime to n, sorry. So except for 1, So 1 and 1, they are relatively prime, but nobody else. Say if you consider 2 and 2, GCD of 2 and 2, that is 2. That's why if it is less than
Yes,
equal
yes,
to,
sir.
then it will certainly include this as well. That's why you don't need to put another definition for phi of 1. That's why it's a more compact form. But in books, they use less, strictly less than, but they also include this. But problem is sometimes the students, they forget to include this one because they just read it and they think that this may not be that important. But unless you put it, it is basically, I mean, it's not complete. So you have to give this value. That's why I have given this way. Is it clear to you now?
Sir, what happen if n greater than equals to 1?
Yeah, so in that case, you don't have any problem. So GCD of 2 and 2, it's 2. It's not 1. Then 2 and 2 are not relatively prime. So in that case, nothing will happen from phi n viewpoint. You can check. Okay, so what is phi of 4? Phi of 4 is number of positive integers which are less than equal to 4 and relatively prime to 4. So who are they? 1 is relatively prime to 4 and 3 is relatively
1
prime to
and
4.
3.
But 4 is not relatively prime to 4. So it will not be counted here, and this value is 2. So if you put less than equal to, it won't be any problem because you are actually considering relatively prime. Clear? But from programming viewpoint, if you are looking at it from programming viewpoint, you have to do basically one extra step. You also have to check for n, but in that case you don't have to check for 1 separately because you don't have to check whether the input is 1 or not. So in that way you can do in two different ways. If value of n equal to 1, then phi of 1 is 1. Else you can have a loop till strictly less than n and then check what is this value. That's all. So mathematically both of them are equally good. So but otherwise if you just put less than equal to, then you don't have to give this part separately. It's already taken care of. Is it clear? Any doubt? Clear to you all? Good. Okay.
Yes.
Yes, sir.
Yeah. So if you have any doubt, please do not hesitate to stop me. I will try my best to explain. Okay. So now it's the sender's setup. So what is the first thing will be collect the values of the public value, public keys, public keys, that is N and E. Then he will convert the plain text, the message M, he will convert the plain text within the range 0 less than equal to M, strictly less than M. So he knows a number and he converts his plain text in such a way that it should lie within this interval. So in my last class, I have described how that can be done in detail. So I just recap those things. So that's why I'm not going in details of all those things. So please have a look at my previous video. There you will find all the details how that can be done. Okay. Then he will calculate the ciphertext. What is ciphertext? This is m to the power e modulo n. Note that m is his own plain text. He knows it. N and E, these two values are public keys. So he has already collected. So he will just make m to the power E modulo n. Whatever will be obtained, that will be send it to the girl as ciphertext. Okay. So the girl will receive the ciphertext C. Now the point is how the girl will decrypt. So this is the key generation step. So this is called key generation step. Key generation step. Sorry, key key gen. This is called encryption. And now it's a time for decryption, and that will be done by the receiver. So decryption. How that can be done? So first thing will be collect C from the sender. Then she has with her the value D. So what she is going to do? She will calculate C to the power D modulo N, and miraculously this value will be equal to M mod N. Note that this value of M is within this range, is strictly less than N, right? So there is no point of writing this modulo N. So this is same as M. So there will be no ambiguity from the receiver's viewpoint. So the girl will retrieve the value of M. Clear? So the question is, what I requested you to learn is the proof of this. Okay, let me explain. I hope that you have already read about it, but let me explain how it is M. Okay, so for that, first have a look at few observations and few important results that we have already discussed in our class 4. In my video, the lecture notes on 4, I have already discussed about few important results. One is the equivalence or the congruence class. So the notation A congruent to B modulo N. So everywhere I am using this. It's very important and it's very powerful notation. For example, say 5 is congruent to 15 modulo 10. Okay, what does it mean? So I will just make a division of 15 by 10 and take the remainder. Whatever be the remainder, they will be here. Okay, so in that case you can say that 25 is also modulo 10. So what is the definition? So this is if and only if a minus b is divisible by n, that is n divides a minus b. So they are equivalent. A is equivalent to b modulo n or congruent to b modulo n if and only if a minus b is divisible by n. So here you can see that 15, 25 minus 15, 10 is divisible by 10. That's why they are equivalent. Similarly, 35, maybe 1005 modulo 5. So they are all equivalent. Clear? But this notation has tremendous power of calculation. How? So it has the very primitive basic properties. What are the properties? One very important property is if A congruent to B modulo n and C is an integer, then A plus C congruent to B plus C modulo n. So you can add the same thing both sides. For example, if you just add 2 on both sides, then you can understand that this is 1007 modulo 5. This property remains the same. Not only addition, you can also do multiplication. Then also this property remains the same. For example, say here, if you want to multiply 10 on both sides, then also you will have this same thing. Modulo 5. Okay. Not only that, if you want to make a power, and that's very much important in cryptography, many times we do power, and that is here also the same thing happens. So you can make a power on both sides, then also the equality holds. And they are very important and uh, very much required in many places, okay, to prove, especially to prove this. So this is first observation. So if you forget about it, I just please go through my previous lecture notes, there you will find lecture videos, there you will find all the things in details. Okay. Another very important term that is known as, it's a theorem, it's known as Euler's theorem. Euler's theorem. What it says, I have already explained, but again, let me recall all the things. It says that let n be a positive integer and a be an integer such that GCD of a and n equal to 1. Then, can anybody tell me what can I write then? Then a to the power something, a to the power, anybody?
Phi n,
Your
sir.
phi n equals
Very good.
1.
Phi n is congruent to 1
1.
modulo n. So this result is very much important, and that will be used in our this theorem. I mean, in proving this RSA equality. And I mentioned about this proof, and that proof is basically based on the concept of Zn star or Un. So I have explained in my lecture video of class 3 and 4 all the mathematical details that will be required for understanding cryptography. So those who miss those classes may read it, or maybe you can read from any number theoretic book. Okay. So now let us come to this proof. Okay. So what we need to prove? We need to prove that to prove say c to the power d congruent to m mod n. Note that what is c to the power d? What is c? C was m to the power e modulo n, right? That was our c. Okay, and what is the relation between ed? Ed is congruent to 1 mod phi n. Note that this is not n, but this is 1 mod phi n. Okay, now from here I need to prove this result, and they are already given. So this part is already given. Okay, so just now, so let's start from here. Okay, so what is ed? ed is congruent to 1 mod phi n. What does it mean? Just now we have checked it. That means phi n divides ed minus 1. That means there exists some integer, some k, such that ed minus 1 equal to k into phi n. That is ed is equal to 1 plus k into phi n, right? And what is phi n? Note that n was p into q, so we know that 1 plus k into p minus 1 into q minus 1. Okay, so let's start with from the left hand side. So it states that c to the power d. Now what is c to the power d? C is nothing but m to the power e. So this is m to the power e, value of c, and 2 to the power d modulo n. That means m to the power ed modulo n. Now put the value of ed from here, say from 1. So this value of ed is this one. So m to the power 1 plus k into p minus 1 into q minus 1. So this is m to the power of this. That means this is same as m into m to the power k into p minus 1 q minus 1. So if by some means if you are able to prove that this value is 1 or something, then you are basically done. Then its value is m. Okay. Now we will consider 2 different cases, or maybe 4 different cases. So what is the GCD of m and n equal to pq? Can anybody tell me? What could be the GCD of? What was given? It was given that the value of m was strictly less than n. If you remember, when the sender was trying to send his message, he has this property: m is strictly less than n. Okay. Now, so the receiver, she knows that m is strictly less than n. Now tell me, what could be the values of these GCDs? How many values could be there?
1 P or Q.
1 p q. And why not pq? Can this value of m be pq? I mean, can this value of GCD of m and n be pq also? Okay, tell me.
M is strictly less than
Strictly
N.
less than.
Okay, then what is the GCD of 0 and pq? Tell me, what is this GCD?
PQ.
pq. And if you remember, the value of m was here. So you have to be mathematically, your observation should be very much clear. So it was 0 less than, so the value of m was 0, also maybe a 0. That also we need to take care of. So we could have 4 different types of GCDs. Okay. So based on that, let us try to find what could be the cases. Okay. So here we have, so let us first consider, let d equal, sorry, not d, let GCD of m and say p is 1, or it may be p, right? Similarly, GCD of m and q, it could be either 1 or q. So how many different choices that we could have? 4 different choices, like, so if I consider this as GCD of mp and GCD of mq, then this order pair could have, so this is the GCD of mp comma GCD of mq. So this is ordered pair. How many values it will take? So it might be, this is 1 comma 1, this could be 1 comma q, this could be p comma 1, this could be p comma q. So that's the 4 different choices that we had. Okay. So based on that, we will prove it. So first, so this case means GCD of m and p is 1, GCD of m and q is 1. Okay. So then m to the power p minus 1, it congruent to how much modulo p? M to the power p minus 1 is how much modulo p? Have a look at
1 mod
oil.
P.
Very good. So this is 1 mod p. Why? Have a look at this result. So what is phi of p? If p is prime, it must be p minus 1. If I put, instead of n, if I put p, then this will be reduced to a to the power p minus 1 congruent to 1 modulo p. Note that here a and n was relatively prime. So here also a and p are relatively prime. So if a and p are relatively prime, then a to the power p minus 1 is congruent to 1 mod p, and that is known as famous result or famous theorem, that is known as Fermat's little theorem. Fermat's little theorem. Okay. So you can understand that Fermat's little theorem is a special case of Euler's theorem. That means Euler's theorem is a generalization of Fermat's little theorem. Okay. So by using Fermat's little theorem, or you can say that by using Euler's theorem, you can have, this is 1 mod p. That implies m to the power p minus 1, and then if you make a k into q minus 1, just now we have seen that if you make a power of something, you can also make a power of something on the right side, but right side was 1, so this again we are 1 mod p. Okay, and what is this value? This is m to the power k into p minus 1 into q minus 1, that is congruent to 1 mod p. And if you multiply both sides with m, then what you will get? You will get m to the power 1 plus k into p minus 1 q minus 1. You are multiplying both sides with m, that's why you get 1 plus in the power. So here also you need to make a multiplication modulo p. Okay, similarly, if q is also relatively prime, so I am considering this case, so here both p and q are relatively prime to m. So by similar result, we can also deduce that m 1 plus k into q minus 1 into p minus 1 is also congruent to m mod q, because p and q are two distinct primes. Now you tell me one very simple result in maybe your class 7, 8, maybe 9 you might have studied, that suppose p is a prime which divides x and q is again another distinct prime which divides x, same x. Okay, then what can you tell about pq divides whom? Pq divides
X.
x. It's very easy. Even if they are relatively prime, then also the same thing holds. But here we have much bigger two distinct primes. Okay, based on this results, what you can say from, say, this is 1 and this is your 2, then what can you say about this 2? So from 1 you can write it like m to the power 1 plus k into p minus 1 q minus 1 minus m is congruent to, or minus m is divisible by p, so p divides this. Similarly, from here q divides m to the power 1 plus k into q minus 1 p minus 1 minus m. See, both the things are same. This one as well as this one are the same. So this is my x, and p divides this and q divides this. So what would be your conclusion? That implies pq divides m to the power 1 q, or maybe in first you can write p, doesn't matter, minus m. And that in turn, what do you imply? So m to the power 1 plus k q minus 1 p minus 1 is congruent to m mod, what should I write here? What should I write here?
PQ.
PQ, and this PQ value is n. And just now have a look at what we have proved. Basically, just try to remember this expression. This expression is exactly the same as the expression we wanted to prove. What we wanted to prove, this one. So what should I write here? This is m modulo n that we have already proved here. So this is congruent to m modulo n. So I just put it there. This is congruent to my m modulo n, and that's what we wanted to prove. The ciphertext to the power d should equal to be m modulo n, and m was my plain text. So C will receive the plain text. Is it clear to all of you? Is the proof, the first part of the proof is clear to all of you?
Yes, sir.
Yes,
Good.
sir.
Okay. The next part is also now almost trivial, but you need to look at the idea. So now what we need to prove now, the remaining cases. Like, so here the case was GCD of m and p was 1, GCD of m and q was also 1. Now have a look at, suppose, GCD of, say, this one. Okay, and what is this case? Can you anybody tell me what is this case? What is the value of m then when this will happen? Value of This is trivial. When this case will occur, when the value of m is how much?
0.
Exactly 0. In that case, you can understand that m to the power this will be 0 modulo n, and that will suddenly be equal to 0, and 0 is same as m. So in that case also all the sides will be 0. So I'll just explain it once again. If this happens, then this means m equal to 0 modulo n. Okay. In fact, this is actually 0, integer 0. Now then m to the power 1 plus k to the power p minus 1 into q minus 1, that will also be, so you are making both side of this power. That means right hand side also 0 to the power this, that means also 0 modulo n. But this is also same as m. So this was our c to the power d. So in that case also we get the same result. C to the power d is congruent to m mod. But this is a trivial case, right? Clear?
Yes, sir.
Good. So now I have two cases, but they are similar looking cases. So I can assume that maybe GCD of something is p and then 1. So this case is almost trivial. Okay. So now assume that let GCD of my m and p is say p, and GCD of m and q equal to 1. So this case, similarly it will happen like it first is 1 and then it is q, the same thing. So it will be 1 and this will be q. The similar way it will follow. Okay. So now since GCD of MP is P, what does it mean? What is the value of M then? What is then P must divide M? If their GCD is P, then P must divide M because M must contain some part of P. Okay. So that means M is congruent to 0 mod P. Okay. That means same as M to the power 1 plus K into P minus 1 Q minus 1 will also same as 0 mod P, because right hand side will again put a power of it and that becomes 0, and that is same as M mod P, because 0 and M are same within this P because P divides M, right? Okay. And GCD of MQ was 1. So in my last section, in my last proof, I have already considered this case. In that case, this one, this was my this value. So m to the power, there also the same thing happens because by Farmer's little theorem. So by Farmer's little theorem, we can also have m to the power 1 plus k into p minus 1 q minus 1 will be congruent to m modulo q. So from 1 and 2, what you can say? PQ divides m to the power 1 plus k into p minus 1 q minus 1 minus m, that is nothing but m to the power 1 plus k into p minus 1 q minus 1 congruent to m modulo p into q, that is equal to n, and that is nothing but our c to the power d. So again we have proved c to the power d is congruent to m modulo n. So we have proved. So all the cases are being exhausted now. Is it clear to all of you? Clear? Any question? Sure. Okay, so what we have proved that, okay, if you are going to have the ciphertext, make a c to the power d, that will certainly be congruent to m modulo n, and this is my plain text. So the receiver will get the plain text. Okay, no doubt. And in my last class, I have already explained how why the attackers is difficult for the attackers to get the value of m, because he doesn't have the idea of p and q. As a result, he is not capable of constructing the value of phi of n. So this is one of the reasons why this is secure. Okay, and so you can understand that till now in real life applications, many real life applications, for example, handshaking protocol, where one browser is going to connect with other browser, how, or having a security in case of a certificate, so there's digital certificates, or even when you talk about for example end-to-end encryption, there also in some forms of this RSA crypto system are being used. So that means in till now RSA crypto system are being used heavily, there is no doubt about that. But still today I'm going to show you few of the very simple attacks on RSA. But these attacks doesn't mean that these attack exist does not mean that RSA is very weak. So this attack actually gives you the idea that RSA should not be used in that way. Okay, okay, let's see. uh, so I have already explained those things. Okay, before going to that, let us first have a look at this book. So I'm now going to give lecture from my book, so Basic Modern Algebra with Applications. So there in chapter 12, you will find all the details of this, like this sketch of the proof, all the mathematical backgrounds are explained nicely in previous chapter, mostly in chapter 10, which will be required for the cryptographic purposes. So the chapter 10 is very important because that is the number theoretic part that are being used heavily in case of public key crypto system, as well as in some cases, for example, in AES, you might know about Galois field. So in my classes, I will also teach about Galois field, how these Galois fields are being used in case of AES. Okay, so that's a block cipher. Till now, it's the mostly used block ciphers. So everywhere when you send some email to some of your friends, everywhere in different forms of AES are being used. So when I will teach that, then I will show you how mathematically rich it is and how the Galois fields are being used there. So all the things are being explained in this book. So this is a book for basic modern algebra with application. The name suggests that this is a book for algebra, but here two chapters are there, chapter 10 and chapter 12 are there, where I have explained all the basic details of cryptography as well as basic number theory that will be required for studying this cryptographic course. Okay. So here, first let us try to find some of the basic concepts that are being used for attacks on RSA. Okay. So let us try to explain a bit how these attacks can be mounted. So you can understand that it's quite exciting. So it's very useful, but still I am going to show you a few of the attacks, then how these attacks are being done. Okay. So it might happen, few cases may happen. Okay. For example, so in case of public key crypto system, when the receiver he chooses during the key generation algorithm, when she is going to choose the N and E, so there might be some problem in choosing E. For example, many of the implement, I mean the person who are going to implement, for example, I'm sure that one of the students here, he has also taken that how to construct this E. So what I in my lecture, what I mentioned, randomly choose some E such that GCD of E and phi n is 1, right? So any E will be sufficient when I choose E, as long as E and phi n is relatively prime. So a natural question is that, okay, from implementation view, why not choosing E from 2, and let's see whether E and phi n is 1 or not. If not, then try to increment by 1 and then try to check whether 3 and phi n is relatively prime or not. Okay, so that could be a very easy approach. So you can understand that if you do like this, then suddenly the values of E will be quite less, because you are trying to minimize the values of E to find it. Okay, now I'm going to show you a very dangerous attack where few conditions are being assumed, and that could be very practical, and it happened in real life as well. Okay, so my assumption is the exponent value, exponent E, is less or small, and and okay, so what we assume? So here we assume that the exponent E is less or small, and the message M is such that M to the power E is strictly less than N. So you are choosing M. For example, one very simple way, when we are going to implement, say, RSA public key crypto system, so what I need from plain text, so from plain text, suppose it's given in this form A, B, C, D. So this is my plain text. I want to convert it into ciphertext by using RSA public key crypto system. Okay, so I have chosen some P, Q, E, and D. Okay, so what we will do, this P and Qs are usually quite big, as usual, usually say at least 10 to 20 digits long maybe, but for practical purposes this will be today's scenario. Each P and Q should be at least 1024 bits long. That means they should have at least 300 to 350 digits within this P and Q, each P and Q. That means P into Q, that means N should be around 2048 bit longs around. Okay, so that's for the practical purposes. So if I, one way, simple way to convert each of these characters into corresponding ASCII value. So for example, the ASCII value of capital A is 65, and then consider 65 to be M, and then consider M to the power E modulo N. Similarly, B is 66, then say this is my M1, then M2 will be, say, M2 to the power E modulo N, and so on. So you can encrypt each of this character, because their ASCII values should lie between this ASCII values. ASCII value should lie between 0 to 255. Okay, so altogether 256 characters are there, which are standard characters. And so you can think of that, okay, each of these characters could be converted into their corresponding ASCII values, and that ASCII values could be thought of as their M1, M2, M3. So for each character by character, you are going to have the ciphertext, and suddenly you will have some, this value will be some C1, this value will be C2, and similarly C3 and C4. So you will send this to the receiver, the C1, C2, C3, C4, and maybe separated by some special character or maybe by comma or something. So when she will receive it, she will just have this C1 to the power E modulo N. She will get M1, that means capital A. She will do C2 to the power E modulo N. She will get back M2, that means capital B, and so on. So that can be done. Okay. So as you understand that, if your value of E is less, for example, say value of E is 3, okay, then
Sir, would it be C1 to e to the power E or D?
oh yeah, it should be D. Thank you. It must be D. Yeah, it should be D. Thank you. Okay, so you can understand that 65 cube, it would certainly be less than if you consider, say, 1024 bit long primes. Okay, so then certainly this will be less than N. So for practical purposes, this assumption is not that bad. With respect to practical applications, this assumption may not be that bad. And many of the students, especially, when they do not know about this attack, then they think that, okay, why not we should start with e from the very base, so from 2 and then try to increment it till we get GCD phi n, and that e should be equal to 1. Okay, so that's a very common standard practice of doing things. So okay, but the point here is, if this is so, then what is our things? So here we have P, we have Q, we have N, we have phi N, we have E, we have D, and M to the power E. For example, assume that E to be 3. Okay, so that is M cube is strictly less than N equal to P into Q. Okay, suppose this is my assumption that some message has been chosen which is very small in nature, such that if you make a power of it, this power is my E, which was also to be a very small one, then MQ is also strictly less than PQ. Suppose the attacker knows this fact. Okay, now what would be your problem? So what is your C? C is M cube modulo N, right? Note that since MQ is strictly less than N, that means C is strictly less than N. As a result, if you can compute C to the power 1/3, then so you can think of this is an as an integer. Why modulo n playing an important role? Because most of the cases this value will go out of n, and as a result when you take a modulo n, then it will suddenly come down within the range 0 to n minus 1. But as you understand this exponent is quite less, then you can very easily make a 1/3, that means cube root of this, and you know that this is an integer. This is an integer, not a modulo n is playing nothing here, because this value is strictly less than n. For example, suppose you are considering n equal to say 100. Okay, and in that case, if n equal to 100, in that case what is happening? Suppose your C value is 96 and another C1 value is 196. In case of modulo 100, both of them are same. So in that case, you will, in that case, C1, whether your C1 or C is 91 or C1 is 190, sorry, 96 or 196, you will have a confusion. So you may not be able to judge whether your C1 is 96 or your C1 is 196, because in modulo n, both of them are same. But look at this important observation, because since this is 96 and you know that this is strictly less than 100, so that means 1/3 of this, 1/3 of C will also be less than 100. For example, suppose this is 27, C1 is your 27 modulo 100, and you know that this value is strictly less than 100. That means your M must be equal to 3, because 3 cube equal to 27, and that value due to the small exponent, so this calculation is very easy. But if this exponent is quite high, quite big, then it would be difficult. That's why today's scenario, it is assumed that the exponent value should be at least 2 to the power 16. That means you should start from 2 to the power 16 at least. If more, it's better, maybe 2 to the power 30 or something. But in that case, you have to might have to work more. That's why how to choose this E. So the choosing of E is like that: choose randomly some integer between at least from 2 to the power 16 and phi n, such that GCD of E and phi n equal to 1. Okay, so that is should be the procedure. Now it's clear. Otherwise, it could be a low exponent attack. So this is known as low exponent attack. Low exponent attack with a small message, such that m to the power e should be less than equal to n. So two conditions are given. One is the message is such that m to the power e is less than n, strictly less than n, so that we can think of as an integer. Another important fact is that this value e is less, so that calculation of c to the power 1 by e is easy. Clear? Okay, so c to the power d, it should be d, right? Okay, no, yeah, m to the power e, yes. So c to the power c is nothing but m to the power e modulo n, and if it is strictly less than, then c to the power 1 by e will be m. So it's a direct attack. Is it clear to all of you? Any question? Any question till now? If you have, please let me know. Okay. So if not, then let's go to another scenario. Okay. So this is known as, again, with small exponent, but it's little more flexible. What it says, so now we extend the attack to the case of arbitrary length message, as long as the same message m, which is sent to multiple receiver with the same small exponent e, but with different values of n. So let us consider this kind of scenario. Okay. Now the scenario is, suppose I suppose this is my question paper, question paper. So, and I want to send it to, say, 3 students. Okay. So I want to send it to my students. Say I have 4, 5, 6, whatever. So all of them in the same course should get a same question paper. So this is my m. Okay. And suppose for my public, I want to encrypt the whole question paper by using RSA Public Key Cryptosystem. Okay. So I have my own e, but what I assume that, okay, I will use the same e for all the participants. But to get more security, what I assume that, okay, I will assume that for each e I have different n. Say for n1, this is my p1 q1. Say for this I have n2, which is my p2 q2. This is my n3, p3 q3, and this is my n4, which is my p4 q4. Okay. So my public parameters are e and d, but this, you can understand that this d values will be changing. So this is my d1 due to change of this n. So for different n's I am using. Okay. So the scenario is like this: I am sending the same question paper to all my students by using the same exponent. Okay. Now my exponent, assume that this exponent is less, I mean small, say 3. So all the cases I am using the small exponent 3, but I am changing my p1 and p2. So p1 q1, p2 q2, p3 q3, p4 q4. But note that all my e's are 3. So you have to choose such a e with such a p and p1 and q1. Okay. Okay. So this is the scenario. Is the scenario clear to all of you? So same message, same m, small e, but pi and qi are different. Pi, qi are different. Okay. Now I have, so same m, but I have in my last example we had this should be less than n, but here we are dropping this concept. That means we are generalizing the attacks. Okay. In my previous attack, it was my assumption, but now I have removed that assumption. It's any m, but I am sending the same m to different students. Now how to attack? Okay. So let the same m be sent to 3 different receivers using the same 3 public keys, n1 3, n2 3, and n3 3. Okay. So the same thing just now I have explained. So with e and n1 is my public, 3 and n2 is my public, 3 and n3 is my public, and 3 and n4 are my public information. Okay. So note that respectively, where PIs and QIs are prime, then the ciphertext C1, C2. So what is my C1 then? For this first participant, my C1 is m to the power e. So e is 3, say, modulo n1. C2 is m to the power 3 modulo n2, and so on. C3 is mq modulo m3, and so on. Okay, respectively. As the ciphertext reach the receiver through insecure channel, the adversary can get hold of this ciphertext. Note that we may assume that GCD of ni nj equal to 1. Why? Can anybody be able to tell me why I assume that GCD of n1, say n1 and n2 equal to 1? If not, what would be a problem?
So since N1 and N2, since they are already cofactored with E, so N1 and N2 has to be cofactored with themselves also, co-prime, sorry, because they share
Yes.
the same E.
No, my question is, what would be a problem? First of all, it's an algorithmic viewpoint. First of all, we know a very simple algorithm for GCD, that means polynomial time algorithm. So in I will may devote 1 or 2 classes on algorithms and how this fast algorithms will be prepared. So as we know that the GCD algorithm that is done by Euclid is very fast, right? And this is polynomial time algorithm. Polytime algorithm. Now tell me, what would be a problem if this is not equal to 1? If GCD of say n1, n2 is not equal to 1, then what would be the problem? Anybody?
So then GCD could be P1 or Q1.
Yes,
Then we can factor. I mean, we can calculate phi n.
very good. So suppose B is the GCD of n1. So what is n1? My P1, Q1, and n2 is my P2, Q2. Okay. Now this D is not equal to 1. What does it mean? What does it mean? So they are different. So they are not same. We have taken different. And their GCD is not 1. Then what will it be? So GCD may be P1, Q1, maybe say P1 or P2 or Q2 or Q1. That means in that case, say N1 maybe say P1, Q1, and N2 say P1, Q2. What will be the GCD? See here, P1 and N1 not equal to N2, right? But GCD of N1 and N2 equal to P1. As just now we have mentioned that finding GCD is very easy. So you can very easily calculate the GCD of two very big numbers. And if you are able to find that GCD is not equal to 1, then suddenly one of the factors must be P1. That means P1 must divide both of them. So it's now very easy to factor them. So what is N1? N1 is P1 into Q1. And if you know P1, then you must know Q1. That means ultimately by just solving the GCD problem, you are able to factor this. In that case, you will able to find phi n. And in my last class, I have mentioned if you are able to find phi n, then you can able to get the value of D, which was the secret to the receiver. So in that case, the security will be broken. That means without loss of generality, we assume that they are not equal to, I mean, the GCD is 1. If the GCD is not equal to 1, then the attack can be done much easily. So we can assume that the when I am sending the question paper, I must be clear enough so that all distinct primes are used in every making this NIs. Either if some of them are common, then the scheme will be broken very easily. So that's what, it's not always that if you are going to use RSA, that means that it will give you security in every aspect. It's not. There are some situations where you need to be little careful. So like this, I cannot use the two primes, say P1 and P1 common here, because in that case the attacker will just make a GCD, whatever be the GCD value, that will be a factor of N1 or N2, and that system will be broken. So we have to be little careful. Now assume that I am smart enough that I have not chosen this PI values or QI values such that this kind of scenario will happen. So now I assume that GCD of Ni and Nj is equal to 1. That means all of them, they are distinct and all the primes are used, they are all distinct. Now can you find some of the algorithms to break it? Any idea? Okay, to understand that, we'll go a little bit of mathematics, but I'm sure that you are very hungry now. So I'm going to show you a kind of sweet. It's in Bengali, we call it Rashogolla, and it's now world famous. So it's a famous sweet from Bengal, West Bengal, and it's a container which consists of many sweets, many Rasgollas. Okay, now the point is, if I ask you a question, a very simple question, if you take 3 rasgullas at a time, and if you take it out, at the end you have only one rasgulla. Means, suppose this container contains many sweets and you are taking 3 at a time, you are taking out 3 at a time. For example, suppose it consists of 7 sweets, and if you take 3 at a time, then after 2 steps, one one sweet will remain inside this container. Okay, similarly, if you take 4 rasagullas at a time, then suppose this, within this container at the end 2 sweets are present, and if you do this same thing for 5 rasgullas at a time, if you take it out from this container, at the end you will have 3 sweets present in that container. So if I ask you a very simple question, what could be the minimum possible number of sweets present in the container? How to solve this problem? Or can you very quickly think of what could be the answer? By hand you can do it very easily, very quickly. That means if you take 3 at a time, it should be 1. If you take 4 at a time, it should be 2. And if you take 5 at a time, that will be 3. Just try to correlate with what does this 1 means, how this 1 is obtained, what is the relation with 3 and the number of sweets inside the box, and that will give you the idea how this can be solved. Any idea, any comments, how many? Quickly you can do it. You may not need to solve the problem mathematically. I'm sure the math students are doing it mathematically, but without doing it mathematically, you can think just what should be the minimum number of possible sweets that can be present in this container. Anybody came up with some answer? Please let me know.
58.
Yes, 58 is the right answer. So that could be the minimum possible. Have a look at this. What is this 1 means when you are taking out of this? So suppose this container contains 58 sweets. Now if you take 3 at a time, then after a few steps, so you can understand that 57. That means if you divide 58 by 3, then this will be the remainder. So 1 will be the remainder. That means you can write it mathematically in this way.
3 mod n should be 1, 4 mod n should be 2, and 5 mod n.
Yes, very good. So mathematically you can write it Suppose you don't know how many suites were there. Suppose x many suites are there. So this is 1 modulo 3. That means if I divide x by 3, the remainder will be 1. Similarly, for 4, it was 2 modulo 4. And in case of 5, it was 3 modulo 5. So they are system of congruences. So there might have some common solution or may not have common solution, but there is a theorem in mathematics, very celebrated theorem known as Chinese remainder theorem. Chinese remainder theorem. In short, we call it CRT. And that actually gives you a confidence that this system of congruences will certainly have a common solution. For example, here you can understand that if you put 58 here, then 58 minus 1, that means 57, that is divisible by 3. 58 minus 2, that is 56, that is divisible by 4. 58 minus 3, that is 55, that is divisible by 5. So it has a common solution. That means if you have this system of equation with system of congruences with a particular property, that each of them, they should be pairwise relatively prime. What does it mean? If you take any two of them out of this, they are relatively prime. For example, 3 and 4 relatively prime, 4 and 5 is relatively prime, and 5 and 3 are relatively prime. So that is the form, and if this is the form, then the Chinese remainder theorem guarantees you that there must be a common solution modulo this 3 into 4 into 5, that means modulo 60. One thing you note that if I have 138, just have a check, 60 plus 58. 60 plus 58 is how much? Not 138, it's 118. So 118 will also satisfy the same property. See, 117. So 117 addition is 9, so it must be divisible by 3. 116. 116 is divisible by 4. 115 is divisible by 5. So you can understand that if 58 is a solution, then anything like 58 plus k into 60, if I vary k equal to 0, 1, 2, and so on, then all of them, each of them will also be a solution of this congruence, this system of congruence equation. That means this system of congruence equations has infinitely many solutions. But when I restrict them in modulo 60, that means 58 plus 60k is congruent to 58 modulo 60. The Chinese remainder theorem says that if you are going to make a product of this and make a mod of the result, then this value will be unique. That means you will have a unique solution for this. Unique modulo this 3 into 4 into 5, that is 60. Okay. That's why if you look at the question that I post, what is the minimum possible number? When I post it minimum possible number, so it must be a kind of non-negative number, and that non-negative number will be unique. But if I ask you the question that, okay, what could be the possible number of suites present in this container, then certainly 118 could also be an answer. 58 will be an answer. Anything like you can put the value of k equal to 2, that means 120 plus 58, that could also be a solution of this Chinese remainder theorem. That means that could be a possible solution of the number of suites present in that container. But my question was, what was the minimum possible number? That's why if you have a mod of 60, then that will certainly give you the minimum value. Okay, so the theorem states that this is the theorem. This is the Chinese remainder theorem, and if you Google it, you will find lots of references for Chinese remainder theorem. if you go a little bit of historical development of this, then you can understand that India plays an important role in proving this Chinese remainder theorem. So it was Chinese remainder theorem, one of the reasons because it was actually the earliest known statement of the theorem as a problem with specific numbers appears in the 3rd century book. This book written by Chinese mathematician Tan Tuzhu, okay, San Tuzhu in his book. But the problem was no proof was there, no algorithm was there. But it was for the first time Aryabhatta in 16th century, he has given a kind of algorithm to prove it. And it's also known that Brahmagupta knew a special case of Chinese remainder theorem. And it's long after that another Chinese, he actually gave all possible proofs, and then it was finally translated in 19th century by some British to today that we know known as Chinese remainder theorem. But you can understand that the first proof was actually given by Aryabhatta in 16th century. So that could be considered as a great achievement for Indian mathematician to work on a problem which we are currently used for our day-to-day life security. So that's very important. Okay, so let's come to the statement of it. Again, I have already explained a bit about it. So suppose you have a few positive integers, say ni's are positive integers relatively prime, so n1 n2 nk, they are pairwise relatively prime, and this a1 a2 ak are any integers, so they are any integers. And so this is a kind of system of congruences, and it says that it will have a unique solution modulo n, where n is the product of n1 n2 nk. And finding that is also very easy. I'm not going to the details of it. So if somebody is interested, he or she can have a just Google, and it's very easy to calculate. Finding these values are also very easy. So this mi and ni's could be calculated very easily, and by using this extended Euclid algorithm, one can find the inverse of something. That can be done very easily. What I want to say that solving this Chinese remainder theorem is very easy. You can do it very good code which can give you the value of the common solution of the system of linear equation. So that means it has a very efficient algorithm to solve it, and based on that the attack comes into picture. So just again have a look at this. So the attacker has this c1 c2 c3 values. So the attacker knows this c1 c2 c3 values. So I think it is somewhere here. Yeah. So the attackers, okay, where it is. Okay, somewhere. So the attackers knows this value. Attackers knows this values of c1, c2, c3. So I'm just again writing. So this is my question paper aim, and the attackers knows c1, which was my m to the power 3 modulo say p1 q1. So c2 is my m cube modulo p2 q2, and say c3 is same as m cube modulo p3 q3, right? Okay, so what the attacker knows about it. So here suddenly when RSA crypto system was made, m was certainly less than n1, that is p1 q1. So m was certainly less than n2, which is p2 q2. So m is certainly less than n3, which is my p3 q3, right? So that's the usual assumption when we prepare our plain text, that should be strictly less than the n value. So what it implies, if I then multiply m cube, that is also less than n1 into n2 into n3, right? Okay. So the attackers has these values, okay, and the attacker knows that it came from some m to per cube, because 3 is my public value and these values are all public. Okay, so you can now write it. So you want to find some common solution. Common solution is m, right? So this is your m cube modulo n1 x congruent to m cube modulo n2 x is congruent to m cube modulo n3. Now see that GCD of Ni and Nj were 1. Now you can apply the Chinese remainder theorem, the similar format. They are pairwise relatively prime. If they are not, then we can mount another attack very easily that you have already seen. So here you can apply then Chinese remainder theorem. What the Chinese remainder theorem says that there must exist a common solution such that that could be your m, say capital M equal to congruent to m cube modulo n1 into n2 into n3. Now note that this mq value is strictly less than n1 into n2 into n3. Just now we have proved it, because each of m is strictly less than n1 into n3. So if you make a product, mq becomes strictly less than n1 into n2 into n3. So this mq is strictly less than this. Now what you will do, you will just simply m to the power 1/3, and that will certainly give you m as an integer. You don't have to think about modulo. Otherwise, modulo could have sent something more than n1 into n2 into n3, then it could have something on another value. But since this gives you the guarantee, which we used it in our last attack where we have assumed that, but now by assuming this kind of scenario, you can automatically find that this mq value is suddenly strictly less than the value of this product. As a result, you can easily make a 1/3 of this and you will get the value of m, and which was your plain text. So you can understand now why we should not use the E to be quite less, and if you do so, you will find lots of attacks. Okay, so I'm now going to give you the most important attack of it, but there is another attack which I'm not going to give you, but I request you to all over to have a look at this. So that attack is another condition is there. One attack I'm leaving for you, but now I am directly going to you the most interesting attack on RSA crypto system. Okay, so let me try to explain the crypto system. So I'm following this book. So this is from chapter 12. So suppose concept is, suppose one very precious image is there. Okay, and say some gallery wants to sell this image. So suddenly they are going it for some kind of bidding. That means in Hindi or Bengali we call it nilami. Okay, so people want to buy, many people want to buy this famous photo. So as a result, when this kind of bidding is being done, so nowadays people are doing it online. Okay, so many people will participate, but they are going to participate it online. Okay, so the company of that gallery, those who are going to organize this kind of bidding, they thought that okay, why not we are going to use RSA, because RSA is very famous and it's very secure. We can use very big primes so that nobody can give some attack. So we'll make some big E so that the small exponent attack will not suddenly be done. And since uh, we are doing it, so the M1, M2 will be different. How? Okay, so what they decided, okay, they are going to bid it and they want to sell it. Okay, so how they are going to do that? So they are first trying to make the infrastructure. That means they are going to do the key generation algorithm. So when they are going to do that, they are going to use this kind of thing. So their private key, they have taken P to be 90001 and Q to be say 90007. So this is a toy example. So you can try with any big numbers with maybe 400, 500 digit long. But here, say here only 6 digit P and Qs are there. So that they are just for a toy example. So I'm sure that my dear students, they also have the implementation of RSA crypto system. Now, suppose they have decided that, for example, suppose they have decided that, okay, this value of this some guy, he has given that 100. So what does it means? So since this is very valuable image, so 100 means 100 million. Okay, and it's not 100 million, so they want in a better way, that's why 100 million euro. So the value is 100 million euro, and what we are going to do is that we are just making it in Indian rupees, and for the timing, for the sake of simplicity, 100 means it is, we are actually multiplying this with 100. Okay, suppose this value is say in current day maybe 1 euro, maybe something around 90 rupees or something. 1 euro, maybe say 1 euro maybe equivalent to 90 Indian rupees INR. So instead of doing some 90 business, what I'm doing, say I assume that 1 euro is equivalent to 100 INR. Okay, so that guy who has given 100, it means actually 100 million and 100 million euro. So we are not using this term million. 100 means it's million. Okay, so what we are going to do is that in Indian rupees it will be like 100 into 100, that means 10,000 million. Okay, but we will put encrypt 10,000. So what this guy says that, okay, so he has given the price as 100, but he is not going to send 100 to the company directly. What he wants, he will convert it into 1000, 10,000, because 100 means actually in our scenario in Indian rupees it should be 10,000. He is going to convert it into 10,000, and then he is going to use the RSA public keys, like here N and E. What he is going to do, he will consider this N and E and computes 10,000 2 to the power E modulo N. Can anybody tell me what is this value? What is this 10,000 to the power E modulo N? Can anybody tell me quickly?
31932
210.
1095368.
Very good. So your implementation and my implementation matches. Okay. So for the sake of clarity, or for the sake of openness, the company has decided that, okay, whatever be the encrypted value they will get, they will post it in the open website. That means they will give a kind of deadline that, okay, this will run for maybe 2 hours or something, and within that hour somebody can bid anything, but that value should be encrypted and that will be kept on the website, so anybody can see this ciphertext. Okay, so as soon as this boy has given this value, suddenly this guy puts some value here. Just after looking at this value, this guy calculates this and sends this value to the website. So now he has given one bidding whose encryption is this. Okay, okay, another girl, suppose she has given 999, so means 99, your aim is 99900 million. Now can somebody tell me, if this is your plain text, what would be your ciphertext? 99900, what would be your ciphertext? It was
47637154748.
748. Okay, so it's also matches with me. But as soon as this girl posted this value to the website, which is the encryption of this 00, suddenly that guy again post some value here. Okay. Now, after 2 hours, when the bidding was done, so the company, they revealed this process. So they are going to now encrypt, decrypt this value, all this C1, C2, C3, C4. So they get 4 bids. Okay. They just did it. So they made this value public so that anybody, this boy, this girl, this boy, they can all check whether the encrypted value, whatever was there, was right or not. That means this boy can check, okay, the decryption of this is suddenly 10,000. That means this boy has given 10,000 as his input. Similarly, from here, he will able to check whether, okay, this decryption of this by using this private key is suddenly this or not. Then he will be able to any kind of confusion that something wrong has happened. Okay, so everybody is quite happy. Now what it can be shown that the person who has given the highest bid should be sold to that, and that has been given to this boy, because the boy has bidded like 2 times, but his bid is more than this girl. Okay, now can you tell me what is this value? So this was 10,000 and this is 10,100, and this is 99,900, but this is 1,0899. So can you guess how much bigger is this value, or how much bigger is this value? How much increase of this value is, and how much increase of this value is? Is it 1% increase everywhere?
Yes, sir.
So here 1% increase of this value, and this is 1% increase of this value. That means in every cases he has increased just exactly 1% of the original plain text. And how it was possible? Even, I mean, assume that this n cannot be factored by this boy. So it can be done with very big numbers, and even if it is whatever big be the number, you can always do this kind of tricks. Okay, so anybody of you, do you want to bid something? Say suppose you want to bid it from, say, 100 to 999 within anything. So can you send me some encrypted value, and then I will try. So you can understand that if your value is, say, 500, then you have to encrypt 500 and then add 2 more zeros. Okay, that means 50,000 in that case. So suppose you want to encrypt, say, 500, then you need to put 2 more zeros, and then this will be your plain text. So somebody try with this. It could be a live game. So one of you think about yourself any plain text value which is, say, maybe within 100 and 999. Think about this and add some 2 more zeros and give me the plain text with respect to this, public key.
Cipher text, sir.
The plain or cipher?
Give me the cipher text, not the plain text.
Okay, sir, 5788.
Just a minute. Okay.
5788
Just a minute. 5788
88 44
44
856
856
214
214. Okay. So this is your ciphertext and this is my ciphertext. Can you please decrypt this ciphertext? It's 88244148371 So everybody, can you please decrypt with this values?
67500.
How much? 67500. 500. Okay, so how much was your plain text? Okay, you can decrypt this one also. You please decrypt this one.
Sir, after decrypting that ciphertext you gave, I got the decryption as 68175.
68175. And what was your plain text?
Decrypted the ciphertext that you gave.
Okay, and what was your plain text?
Text was 67500.
67500. Yes.
Yeah.
So you can see that 1% increase I have made. So 67500, 675, 57186. So now you can understand 1% I have given, whatever you gave me the value, I have given 1% increase of this. So what is happening? Is it clear? Is it clear to all of you? So he has given me one ciphertext. This ciphertext he has given. Sorry, I think the ciphertext is here. Yes, he has given me this ciphertext. I think this ciphertext was given by you, right? This one?
Yes, sir. 5788. Yes, sir.
Yeah. So this ciphertext was given by him, uh, of which the plain text was this one. And when I received this ciphertext, I gave another ciphertext, this one. And when both of them are decrypted, one value came out to be, his value came out to be this, and my value came out to be this. And it can be shown that it is just 1% increase of his value. So suddenly I have, without having the plain text, I have increased his plain text by 1%. So how this miracle happens? And that is known as bidding attack, and that's a very important attack on RSA. So it's not a weakness on RSA, but it says that do not use RSA for bidding scheme in that way. You could have used this, but that your strategy should be different. Now the question is how this is happening. Is the attack procedure clear to all of you? Now I'm going to explain how this is happening, and it's very exciting. Okay. So what is happening here? So the company has given the values of public value, this N and E. So the attacker knows this value N and E. The attacker also knows the first participant, say, who has given C1, which was nothing but M1 to the power E modulo N. One thing you note that encryption of message, say encryption, say EN encryption using the message of RSA, how it works, say M1, M2. That is the most important observation for RSA encryption function. So if you consider En of M1 into M2, how it will be written? So this will be M1, M2 to the power E modulo N. And this is equal to M1E modulo N into M2E modulo N, because this form is a homomorphic function, and that is encryption of M1 into encryption of M2. So encryption of M1 into M2 is same as encryption of M1 into encryption of M2, and that is the basic trick here that the attacker has used. Let's see how. So attacker knows C1 equal to M1 to the power E modulo N, right? Now what the aim of the attacker? The attacker wants it to be, say, 1% increase of it, say 10% increase of it. For the sake of simplicity, suppose the M1 value was my 100, okay? And the attacker wants that M2 that he wants to produce is 10% increase of this 100, then what should be this value? If you want to have a 10% increase of 100, then what should be the value of M2?
110.
110. Now, how you calculated this? So initially you had 100 and then 10% increase. How did you get this? So 10% means this into 100, right? That's why you get it cancelled and you get finally 110. Is it clear to all of you? How did you get this? 10% increase mean what? Is it clear?
10% of M, then add it to M.
Yes. So now can you think of how I made this? So what is happening here? So everything is in mod n, and this mod n is a product of two big prime, P and Q. Suddenly P and Q are not equal to 2 and 5, right? Then GCD of n and 10 should be how much? GCD of n and 10 should be how much?
1.
1, because P and Q are not 2 or 5. So within this n, you do not have neither 2 nor 5. So here only 2 and 5 are factors are there. So the GCD of n and 10 will be suddenly 1. So as a result, you can suddenly have inverse of 10 in Zn star. So what does it mean? Un star. That means when you will have a GCD, in my video lecture 3 and 4, I have explained with details that when you will have some, say you have 10, you will not have, for class 2 you cannot have inverse, for class 4 you cannot have inverse. So whose inverse will be there? The inverse of 1 will be there, inverse of 3 will be there, inverse of 7 will be there, inverse of 9 will be there. So all those elements which are relatively prime, GCD of all those elements with 10 is equal to 1. That means if they are relatively prime, that means if their GCD is 1, then suddenly their inverse will exist. As a result, in Zn star, inverse of 10 will suddenly exist. Okay. Now, so you know C1. So C1 is your M1 E modulo n. What you need to do? You know E, you know 10 inverse, you know how much you want to increase, then we'll able to stop you. So you are calculating C2 equal to M1 to the power E, then so is your say 100, if you want to make it 110 to the power E, and then inverse of 100, inverse to the power E. So if GCD of n and 10 is 1, GCD of n and 100 is also 1. So you can calculate inverse of 100 inverse of E modulo n, right? Then you can see that since this is encryption of everything, so M1 into 100 inverse into 110 to the power E modulo n, and that is your C2. This is your C2. And when they are going to decrypt it, for example, if you put here 100, when they are going to decrypt it, how much they will get? 100 into 100 inverse into 110 to the power E, and when they are going to decrypt it, that means to the power ED, and we have already proved this will be same as M, and this will be get cancelled, this value will be 1, 100 and 100 inverse, this value will be 1. So what you will get? 100 10 when you are going to decrypt this. That means when you are doing c to the power d modulo n, that value will be basically this value will suddenly come up, and this value is nothing but 110, which is 10% increase of your m. Is the idea clear? So that is the problem of homomorphic encryption here. That does not mean that RSA is a weak system, but it shows you that when you are going to use RSA, then you have to be little careful, and you cannot use directly in bidding process, not an attack. In bidding process, you cannot use directly in that way. So you have to devise your system in such a way it should not be able to use or manipulate this homomorphic encryption property. So this property is known as homomorphic encryption property. Naively, this property. So encryption of this equal to encryption of this into encryption of this. So that is a very strong property. Many places that can be used as an application, special property, that could be an advantageous position. But here, especially in case of a bidding, this could be considered as a disadvantage. Any question if you have?